Okay, the next task was to construct a graph such that when the value of x doubles, the value of y triples. Now, here we did a little bit of talking about what that could mean, but we then went up to the board and actually constructed this graph. And that's what I'm going to talk about here. Okay, so first of all, you say when x doubles, what does it mean for x to double? Now, people originally sat down and wrote a number of x values, like 1, 2, 4, 8, 16. People understood what it means for a number to double and did that sort of thing. So we saw people writing down tables. You got x and you got y. Okay, so let's say x is 1, 2, 4, 8. Okay, those are doubling values of x. Now we want y to triple. Well, one way to make y triple is to start with y equals 1 and then multiply by 3 at each step. And here are y values that triple whenever x values double. Now, we don't really want to do this with numbers, although if you did this and plotted these points accurately and did a nice smooth curve, you would get something that is every bit as good as what we have here. But we want to learn to do this kind of visually. So we started out by marking off an x, maybe a very small value of x, and then asking people one at a time to come up and show what happens if x doubles. Now, for example, if this is your value of x, then if x doubles, well, the value of x is represented by the distance between my fingers, because, of course, x is the distance from the origin out to the point. If this was a value of, let's say, 14, then this distance would be 14 units. And if we wanted to double that, we would add that to what we already had, and we would get this point. Now, we don't have to think in terms of numbers. We just think of this geometrically. We take this value of x, we double it, we get this. Now, what's the value of x? Well, it's here. So here is our value of x. If we double it, we're about here. Now, these aren't drawn with complete accuracy. People did this the best they could. Here's another value of x. If we double it, we get out to here. Well, that's a little too far, but that's okay. We get the idea that these values of x, excuse me, had to pause there. I think I got that cleared out. These values of x appear to be doubling. So another way that we did this, and the way we actually constructed this graph, is we made a mark here, and then we estimated halfway back. So we moved back by halves each time, which means that if we were moving in this direction, we would be doubling the values. So, in any case, we've got a series of doubling x values, and there are several of them in here where the chalk marks get almost too wide to distinguish one from the other. Okay, then we have y values that are tripling. Well, here's the first y value. It's a little hard to see, but if we go 1, 2 more, that looks like it about triples. And from here we go 1, 2, 3. Actually, tripling might be about here, but we're not going to quibble. We're just trying to get the idea. And then from here, one of these, and 2, and 3. Well, that's a little high. This is a little more than 1/3 of this, but this is a reasonable attempt. Okay, so. And the way we actually did this is we started here and said, okay, go 3 times as close. Well, actually, I didn't say anything. The student figured it out. I could see the student doing this and this. So it was clear that the student did exactly what they were supposed to. Ended up getting that value a little bit high, but that could be due to the angle at which he or she was looking at the board. Since we seem to have an all-female class this year, it was a she, but we get the idea that we could mark this off in units that increase by a factor of 3 each time. They get 3 times as great each time. Now, if we do that, then we can get a graph of that satisfies the condition that y triples when x doubles. We can actually get several graphs of that nature. The first graph we did was this one. And in order to get this graph, I started off by marking a point right here, where this unit here, which is not the first x unit, which is not the first x unit that we saw. And actually, I think I started here. Okay, and the y unit's very small here, so I made a little x here in orange. And then I had students come one at a time and mark the subsequent points. Okay, so if this is our first x value here, and gee, I don't have the right color. I'm going to pause for a second. Okay, now here was the first x value we used, okay? It's directly above this little mark. And the first y value we used was the smallest division we had, which is very small, almost down to the axis. So we got a point here. That was our starting point. Now, we want y to triple when x doubles. How are we going to do that? Well, here's our x value. If we double it, we get, well, that's going to be the next x value. Here, x is doubled. And now the tripled value of y is here. So we have a point up here. Then if we double x again, we go from here out to here. That doubles x, and we want to triple this y value, which gives us this y value. And now you can start to see things. We get this point. Then we double x again. X is here, doubled, it comes out here. Here's our y value. 1, 2, triple it. We get this value, giving us this point corresponding to this doubled x value and this tripled y value. And then we double x again, we get out to this point, we triple y, and we get up to this point. Now the graph, I drew that. That was my drawing. The graph kind of had a little glitch there. It's not very well drawn, but you get the idea. It's increasing, and it's increasing faster and faster. We did the same thing in green using a different starting point. Okay, we used the same y value that we started with before, but we used a smaller x value. We used this x value. So we had a point here. Now, what difference does that make on the graph? Well, when I double x, I go to here. When I triple y, I go up to here, which is the same y value we used for this point. But of course, that makes the graph a little higher than it was before. Then when we double this, we triple y again, we get this value, and we follow the same procedure. We get a curve that has the same description. Y triples when x doubles. But the graph looks a little different. It's steeper, it's narrower. And you can see the curvature a little better. Okay? Now, again, both of these graphs obey the same rule. Y triples when x doubles. I could have drawn another graph, and I'm going to stop and do that just for point of reference. Okay, in purple, I've drawn a new graph. Now for the starting point, I chose this x value and this y value. So you can see we've got purple here to indicate that we're using this x value. The same thing we did for the orange graph, but I'm using a bigger y value. So compared to the orange graph, I've had a couple of triplings to get up to this point. Having done that, then I just follow the same algorithm. When I double x, my y value triples up to here, and we get this point. Doubling x again gets me out to here, and the y value is up here. So I get another graph. Again, they're all essentially the same graph, because I haven't put any numbers down here, and I haven't put any numbers up here. I could relabel this graph, and I'll do that in a separate video just to show how this might be used. But we understand that there is a certain class of graphs where y triples when x doubles. And the only difference is how far we spread it out this way or how much we compress it in this way. Or alternatively, how far we pull it out this way, stretch it this way, or compress it this way.